Right, so now I'm going to talk about the Bohr model. So Niels Bohr proposed a model of an atom in which electrons could only occupy certain orbits, could only occupy orbits of certain radii. And his model was based on three assumptions. Firstly, electrons in an atom exist in stationary states. Electrons may move from one stationary state to another by absorbing or emitting a quantum of electromagnetic radiation. And thirdly, which is the most important one, the angular momentum of an electron in a stationary state is quantized in integral values of h over 2 pi. Now I'm going to talk about this third assumption as I find it really essential. Alright, so so what do I mean by quantization of angular momentum? So the angular momentum of an electron in a stationary state, so basically when it's not emitting or absorbing energy, is quantized. In other words, it can only have specific discrete values. And the angular momentum for an electron is given by the following formula. L, which is the angular momentum, is equal to n times h bar. H bar is equal to h over 2 pi. So instead of writing h over 2 pi, we just write h bar. And from option B, or from chapter 6, right, we know that angular momentum is equal to I times omega, or I is mr squared, and omega is v over r. The r's cancel out, and we'll be left with r times mv. So I can rewrite our first equation by substituting r times mv for L. We'll be left with rmv is equal to nh bar, right? Now, we know from de Broglie's hypothesis that every moving particle has wave-like properties characterized by a wavelength lambda. So from de Broglie, we know lambda is equal to h over p, where p is the momentum of the particle. And so since momentum is it's mass times velocity, we can rewrite this in terms of momentum, and we'll be left with r times p is equal to n h bar. And p, from de Broglie's hypothesis, is h over lambda, which can be substituted in this equation, and we'll be left with r times h over lambda is equal to n h over 2 pi. The h's cancel out. We'll be left with lambda is equal to 2 pi r over n. And 2 pi r is the circumference of the radii. And you can also write this in terms of n pi. So 2 pi r is equal to n pi. And this equation right here, this expression that we have, where n can be equal to 1, 2, and 3, is really similar to the one we learned in chapter 4 about standing waves. And so Bohr's condition that the angular momentum has an integer multiple of h bar was later reinterpreted in 1924 by de Broglie as a standing wave condition. And so the electron is described by a wave, and a whole number of wavelengths must fit along the circumference of the electron orbit. And so, And so for an electron to exist in a stable orbit around the nucleus, it must form a standing wave, a wave that remains in a constant position. This requires that a whole number of wavelengths fit exactly into the circumference of the electron's orbit, which is 2 pi r.